Hey everybody, welcome to the third lecture for Math 131. Today we're going to talk about a little bit about inequalities, and then the rest of the time we're just going to be talking about sets. To begin, let's start by talking about inequalities. And since this is going to be a review for almost everyone, I assume, I'm going to make this pretty brief. If we look back to high school and middle school, we'll remember that inequalities are a way of describing the relationship between values. The notations are as follows. We use this sort of a V shape for less than, greater than, less than or equal to. We have a line underneath, and then greater than or equal to. And as an idea of what that actually looks like in practice, we might say that 4 is less than 5, so it's quite literally going to be read exactly the same idea, or the same way. And in the case that we say, let's say we've got x, and we know x is greater than 12, greater than or equal to 12, I should say. Well, then that implies x could be 12, 13, 14, it could be 12.1, it could be 13.4, it could be whatever number we want it to be, as long as x is greater than or equal to 12. That's the general idea of inequalities. Like I said, I kind of assume most of us remember this. If we have any questions about this, by all means, please shoot me an email, ask. I'll be happy to help with that. However, having said that, let's move on to sets. So, to start off talking about sets, we probably should start with the definition of what a set even is. So like you see over here, a set's really just this idea of a container of things. And those things we call, in particular as they relate to the set, we call those the elements or members of the set, right? So one example we can think of would be a library. A library can be thought of as a set of books. Now, having said that, we also have this idea of subsets. A subset is another set such that every element in it belongs to another set. So as an example of this, we can think of the philosophy section of a library as a subset of the entire library. Because every book in the philosophy section, they all belong to the library. So in that way, like I said, we can think of the philosophy section as a subset. Now as a more rigorous example of what a set is, let's consider this example we've got here, a year. So we've got a year, and we're saying a year is the set of day 1 all the way through days 365. Now I want to point something out. If we notice, year is what we're naming the set. The set is actually everything in between the curly bracket. And each day is the element of the set. So day 1 is an element, day 2, day 3, so forth and so on, all the way through day 365. But together, they make up the sets. And when talking about sets in math, we use these curly bracket notations. So this is the general idea of the basics of what we're going to be talking about, right? It's this idea of a collection of objects, of things, that we call elements. They're going to have this idea of subsets at some point that we're going to be talking about. And generally, we're going to write them looking something like this. In just a minute, I will have that up on the board for y'all. So, before we get too much further talking about sets, it probably help to know there are 3 particularly common sets that we're likely to run into in this particular class. To begin with, we've got the empty set, which is a set that is exactly what it sounds like. It's a set with nothing in it. The empty set is an empty set. We also call it sometimes null or nil. We have the set of natural numbers, which are all the traditional counting numbers, right? 1, 2, 3, 4, all the way on forever, right? We also have the set of real numbers. Real numbers are literally every number between negative infinity to infinity. So it could be negative 455. It could be 3,900.1114. It could be whatever we want, any number, as long as it's not negative infinity or infinity. So, having said that, let's start talking about how to actually write sets and quote, build sets. To write a set, we oftentimes use what's called set builder notation. As you can see, we have these traditional curly brackets, just like I had said previously. We will always use curly brackets, always, 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 always use curly brackets to denote sets. From there, we've got these two parts divided by a line. Now, this first part, this is going to tell us what our elements are. This line, quite literally, is just the math notation for the terms such that. And the second part, it's just the instructions for how to choose the elements of our set. So as an example of this, let's say we want to look at age, right? The age of a person is going to be any real number such that it's 0 or greater. So what we're saying is age is elements of real numbers such that they're greater than or equal to 0. Now this brings up another point I want to make. Notice this funny E thing. In case you can't see it well, this funny E thing looks like this. Looks about like this. What it means is elements of. And that's quite literally all it says. It's elements of. Okay. So, we know what the set of ages possible are. Cool. Now we might want to look at different sets of ages, like the ages of adults. Well, the ages of adults are going to be all those ages such that the age is 18 or older. Okay. Similarly for kids, it's going to be all of those ages such that the age is less than 18. Now, before I go any further, I want to write something up here really quick, just to give you vocab, just for the sake of vocab really quick. So I just said this is all called set builder notation. This is one way to define a set. We also have what's called roster method, which is quite literally what it sounds like. So when I wrote the set of natural numbers before, I wrote it using the roster method. I said it's the numbers 1, 2, 3, and on forever. This is called roster method. This is called the set builder notation. Both are equally good ways of writing sets. There are going to be times where this is more convenient to use than this. That's really the only reason I wanted to point it out. Having said that, let's move on. So, this now brings us to the idea of cardinality, or the cardinal number of a set, which by definition is the number of unique elements in a set. And it can be written in one of two ways. Either like an absolute value, so with one line on either side of our symbol for the set, or we have n of s. So write it like in parentheses with our set inside. This is the way the book writes it. And I will probably jump back and forth as I think about it. So just so that you know, there are two different types of ways of writing this. They mean the exact same thing. This, of course, like I just said, is the way the book writes it. Now, as an example of the cardinality of a set, let's say we have this set up here, A. It's the set with elements 31, 2, -3, 4, and 55. Now we want to know what the cardinality is. So we're going to have to count the number of unique elements in the set. All right, cool. 1, 2, 3, 4, and 5. Cardinality is 5. Cool. Now in the case of this B, this set B, we've got 1, 2, 3, 4, 5 elements, but they're all the same number. All of them, they're all 3. So we only have a cardinality of 1. And in the case of the set of natural numbers, we've got 1, 2, 3, 4 on forever. So the cardinality is infinity. Now I want to point something out between these 3 sets here. These 3 sets, they have a finite cardinality, right? It's a finite number of elements in it. This one, however, does not. It's because of this that we say these 2 sets are finite and this set is infinite. So, in case you ever hear me say, is this set finite or not? Well, just check the cardinality. Is it a finite number? Yeah? Cool, it's finite. If not, no. Having said that, let's get on with this idea of equivalent and equal sets now. This is gonna suck, and I know that, and I'm sorry for this. But an equivalent set is not the same thing as an equal set. So bear with me for just a little bit. An equivalent set is only a set, or only 2 sets, whose cardinality are the same. So let me say that again. We've got 2 sets, A and B. If their cardinality is the same, they're said to be equivalent. Set A and set B are not equivalent sets because their cardinalities are different, right? Equal sets, on the other hand, well, an equal set is 2 sets who share all the exact same elements. Every last element is the same. And for those, we write A equal to B. Pretty straightforward now. Having said that, let's look at a couple of these examples that I've got over here. But first, I am going to erase this. All right, so we've got the set A with elements 4, 5, and 6. We've got the set B with elements 6, 5, and 4. We've got the element C, we've got the set C with elements 4, 5, and the empty set. And we have the set D with the elements 4 and 5. All right. So, looking at these, there are 2 equivalent sets, or 2 equal sets, my apologies. The set A and B are both equal. They have all the same elements. It doesn't matter what order they come in, they have the exact same elements. If you were going to list them out, they would have the identical list. All right. From there, we've got 3 equivalent sets, A, B, and C. Because A, B, and C, all 3 have the exact same cardinality. And then we got D here. D is one I want to focus in on for just a second. Notice D is a subset of each of these, but it doesn't have the same cardinality as any of them, and it's not equal to any of them. So we say D isn't equal or equivalent to any of them, but it is a subset of all of them. Having said that, brings up the next topic, more about subsets. Give me a second to write this up and get right back to you. So, as we said earlier, the definition of a subset is a set such that every element in it is also in the other set. So, as we've got here, if every element of B is in A, then B is a subset of A, right? Okay. Well, because we're mathematicians, we want to write this in shorthand notation, and we use this notation here, this sort of sideways U with a line underneath it to say B is a subset of A. Cool, fair enough. Using this definition, let's move forward and look at this definition of proper subset. If our sets aren't equal and B is a subset of A, then what we've got is B is a proper subset of A. And we write that pretty much the same way, except we don't have that line underneath the sideways U. So what does this mean? Well, let's look over here. We've got this example up here with three different sets. We've got the set A, 1, 2, 3, 4. Okay. We've got the set B with elements 1, 2, 3. Okay. We've got the set C with the elements 3, 1, 2. Well, looking at this, we can already see that B and C are subsets of each other, and that they're equal. Okay. So B and C are subsets of each other. Notice though, excuse me, that A and B, they're not equal to each other, right? But B is a subset of A, just like what we've got here. But because they're not equal to each other, then we know that B is a proper subset of A. So all this idea of a proper subset means is that there's a missing element, at least one missing element. In our particular example, B is missing the element 4. But that's really the difference between a proper subset and a subset. From here, we're going to move on to power sets. It's more about cardinality. Give me another second. I'll write this. Finally, getting on to this idea of power sets. All a power set is the collection of every unique subset that you can make from your original set. So, what that literally means, for example, is like what we've got here with this set A. Before I go and show that how to find this power set, I want to point something out. The empty set is a subset of every set. Because we can always say there's this missing unspoken element that's there, and it's the element of nothing. Which I know is a really weird idea, but we're going to have to take it at face value. The empty set is a subset of every set. All right, so when we take the power set of this set A, which contains the elements A, B, and C, we're going to have the set of the sets, empty set, the set with only element A, the set with only element B, the set with only element C, the set with element A and B, the set with element B and C, the set with elements C and A, and the set with elements A, B, and C. All right, so what we've done is we said how many unique subsets can be made with this? How many unique organizations can be made? Nothing. 1, 2, 3, each of them by themselves, each combination of 2 of them, and then the combination of all 3. And if we wanted to know what the cardinality of the power set's going to be, I want to point something out here. Notice that here we have a cardinality of 8, right? Well, 8 is equal to 2 to the third. Well, 3 here, 3 is equal to the cardinality of our original set. That's because the cardinality of every power set will be 2 raised to the power of the cardinality of that original set. Having said that, imagine if we wanted to know what the cardinality, well, I shouldn't say the cardinality. Imagine if we wanted to know how many proper subsets, we can make from A. Well, that's just like asking the cardinality of our power set if we remove this very last set here, right? Because all the rest of them are proper sets of A. If that's the case, then it's going to be the cardinality of the power set minus 1. And having said that, that's all I've got for y'all. If you have any questions, please feel free to let me know. I will be trying to make the next lecture either today or tomorrow. Have a good one, guys.